Today I'm going to give a talk about catalytic and electrochemical reactions of cyclopropanols. Generally speaking, I'm going to speak about development of new chemical reactions and why new synthetic methods are so important. So generally, it's generally speaking, development of new chemical reaction is a crucial element of chemical science because we require, when we do chemical synthesis, we try to synthesize big and demanded molecule. We require methods that works perfectly, that enables us to perform this synthesis in a small number of steps, in high yields, and we require methods that atom economical methods that allows us to not to use this. Okay. Methods. Oh, I'm so sorry for this. We need atom economical methods, and let's begin. Now, why cyclopropanols? Why am I going to talk about cyclones? Why are we working with cyclopropanols? There are three reasons. The first reason is that cyclopropanols are reactive, and it's easy to find new reactions of these molecules because they contain this strain ring. The second reason is that they are easily available. They can be easily synthesized. They can be easily synthesized from the esters and Grignard reagents or alkenes. And the third reason is that not only is their chemistry is not only as reactive, but also the reactions are diverse. So if we want to synthesize diverse molecules starting from the common precursor, this is an ideal chemistry for this aim, to achieve this aim. Working on synthesis of biologically active compounds, we face lots of problems. With lots of problems, we face the problem that we need new synthetic tools. In fact, when we worked on the synthesis of syncoestrol, we've been working on this problem now. We face two problems. With the chemistry of hydroxycyclopropanes, and we required to solve it. The first problem was that when we tried to obtain this bicyclic ketone. This bicyclic ketone is this purple part of the target molecule. We required to carry out this transformation. We required to transform this cyclopropanol to the ketone. This kind of reaction was kind of known, but according to the described procedure, the outcome of the reaction was not that good as was expected. As the reaction proceeded in low yield, inseparable by products forms, and moreover, toxic reagents and stoichiometric quantities were required to carry out this transformation. Another problem we faced during this synthesis is the problem of the two parts of molecule assembling of the cross-coupling problems. When we tried to assemble this purple block with another part of the molecule, the best reaction was the reaction between vinyl triflate and this fluorobrate, alkyl fluorobrate, catalyzed by palladium. And this reaction proceeded perfectly. But there was one trouble. One trouble was that this coupling partner, the best way to it was through a three-step way, starting from this hydroxycyclopropane. 3 steps is not good in terms of step economy. And we asked a question, whether it would be possible for us to couple this cyclopropanol with vinyl trifluoride directly. By the time, the methods for the coupling of cyclopropanols with vinyl bromides or vinyl trifluorides, they did not exist at all, but we did it. And I'm going to tell you about it today. It was the first our project where we found out that we need new synthetic tools, we need new chemical reactions. And another project was the synthesis of steroids with anti-cancer activity. Our aim was to synthesize steroids with this core and diverse side chains. Recently, we find that such kind of cyclopropanols can be easily obtained. We published this 3 years ago. This cyclopropanols can be easily obtained from alkenes and esters, and the more diverse reaction for the re-opening of cyclopropanols we have, the more diverse compound for testing the biological activity we have. So with these ideas in mind, we started to develop new synthetic methods of the ring opening functionalization of cyclopropanols. And we started with the project when we managed to apply cyclopropanol as an equivalent of enone in CH alkynylation reaction. Next, we developed a sustainable protocol for the ring opening bromination. This reaction proceeded electrochemically. And then we developed 3 photochemical reactions. It was ring opening isomerization of cyclopropanols to linear ketones, an oxidative ring opening of cyclopropanols, which lead to alpha beta linear unsaturated ketones. And finally, we accomplished this goal. We reached that goal. We managed to couple cyclopropanols with vinyl halides or aryl bromides under the photoredox condition. That's what I'm going to tell you today. And let's start with CH activation reaction. Recently, we found that this orange group in the molecule can assist palladium catalyzed CH acetoxylation of real acetic acids. You can see that this molecule can be transformed very fast, quickly, rapidly, within 40 minutes to this deacetate. How it works? At the beginning, this directing group coordinates palladium. Now it is closer to the CH bond. And when it floats somewhere next to the CH bond, the reaction occurs, the reaction that leads to this cycle. And then the bond, carbon-palladium bond, undergo oxidation with vinyl iodine acetate. And this happened twice, for the one CH bond and for another. This directing group we developed, it was as a group that promoted the reaction, this reaction with the highest speed, with the highest rate. At 100 degrees, it took 40 minutes for the reaction to reach completion. And this directing group even catalyzed CH acetylation at room temperature. It's not shown on this slide. But what was the next question? It was our next question. Okay, can we engage this intermediate in Heck reaction in not only CO bond construction, but also in carbon-carbon bond construction? And it really did work. It really did work. When we mixed this starting amide with palladium acetate, with alkene, and oxidant is required for the Heck reaction, we obtained this compound. And then the question was, okay, we mix the substrate, palladium acetate, and oxidant. Under the same condition, it was reported by Professor Cha, cyclopropanols undergo oxidative ring opening to give vinyl ketones. And our question was, can we do something like that. Can we mix cyclopropanol? Can we, with the substrate, add catalytic amounts of palladium acetate and inoxidide and obtain this the product, this phenylation product. Why should we use cyclopropanols instead of enons? Enons are not commercially available and they are quite unstable. But cyclopropanols can be easily prepared from the esters. Carboxylic acids and their esters is a cheap source of cheap starting material for the organic synthesis. So cyclopropanols can be easily obtained, and they can be engaged in reaction with CH activation reaction into the CH alkylation as a coupling partner, as a synthetic equivalent of alpha beta unsaturated ketones. And it really did work. We use this cyclopropanol. Cyclopropanol burned unprotected hydroxyl group. So this reaction was quite, this functional group was tolerated under the reaction conditions. React is with the aryl acetic acid modified with the directing group we've developed. And in the presence of catalytic amounts of palladium acetate and oxidant, benzoquinone is used as next state in acetic acid, 90 degrees Celsius, we obtained the product. We obtained the product in 44% yield. It really did work. And what else should I say is that we also could modify a little bit this reaction. We, instead of one-step reaction, we used two-step one-pot protocol. It let us increase the yield from 44 to 50%, little increase, but we were happy that it was higher. Under this modified conditions, we investigate the scope of the reaction, and we find out that different cyclopropanols containing different functional groups, containing hydroxyl, the steroidal part can react, and aryl acetic acid can react too, including not only benzene, those containing benzene, but also indolyl acetic acid can react under these conditions too. So this was all about the palladium catalyzed CH activation reaction, and I'm going to talk about other reactions. And in this method, we used monosubstitute cyclopropanols. But when we use desubstituted cyclopropanols, this molecule is more sophisticated, it's more interesting. Why is that? It contains another substituent and this carbon. And when we speak about opening reactions, there are two options appears that either red CH bond can be cleaved or black carbon-carbon bond can be cleaved in this reaction. And moreover, this molecule is chiral. It contains two stereocenter, and it can react with electrophiles. In this reaction, proceeds with cleavage of the red bond. And what's interesting about this reaction is that the stereocenter, which was in the cyclopropanol, it stays in the molecule. It's not undergo destruction. And what reaction we investigate the bromination, the electrophilic bromination of cyclopropanols. And this is non-reaction, but previously it was suggested for this reaction to the use of bromine, molecular bromine, or n-bromosuccinimide. And these reactions are quite aggressive. And moreover, n-bromosuccinimide is not ideal reagent in terms of atom economy because it contains extra atoms. And we thought that we can substitute this, we can generate bromine cations during the electrolysis of magnesium bromide salt. And it really did work. And another problem we investigated that further application of this bromides, because when we synthesize bromide from the chiral cyclopropanols, we obtain the chiral product. But previously, these molecules were used in synthesis of enons. The application was limited to this, and it's lost. We lose this chiral stereocenter. It's not ideal application of these molecules. So if it is possible, we wondered if it would be possible to use these bromides in cross-coupling to obtain chiral to obtain chiral ketones. And this is what we did. First of all, we optimize the conditions for the electrolysis, and under this condition we managed to obtain not only bromides but also iodides. Reaction proceeded in very high yields, up to 99%, maybe it's highest yield, and we obtained different bromides, iodides, and we used chiral molecules. We used chiral molecules. The stereocenter did not disappear. It stayed in the molecule after the reaction. Different functional groups tolerated this reaction, including the hydroxyl group, bromine group, and silyl protected group. All this tolerated this reaction conditions. And having synthesized these molecules, we included this chiral bromide, this chiral beta bromo ketone. We decided to investigate if it would be possible to couple them with to engage them in cross coupling, and it really did work. Cross coupling proceed. This is a classical method of the cross coupling of halides, and there's copper catalysis. We substituted bromide with alkyl chain. Then we used this in reductive catalysis. Reductive cross coupling worked very well too. In this reductive cross coupling work too, we obtained alpha, beta, gamma, delta unsaturated ketones containing one stereocenter next to the carbonyl group. It's very sensitive stereocenter. It's hard to, it's not easy to obtain such compounds. And a relation reaction, the reductive coupling with aryl halides, it's photochemical photoredox conditions, Professor Macmillan conditions. It allowed us to, this reaction allowed us to obtain this alpha beta aryl substituted ketone. So worked perfectly. So we have new method for now we have another method, another new approach that allows to transform cyclopropanols into something valuable. And next, I've already talked about CH activation, about electrochemistry, and now I'm going to talk about photochemical reaction, about redox reactions of cyclopropanols. And metal photoredox catalysis, it dramatically changed the field of cross-coupling. This is the work by Professor Macmillan, published in Science in 2014, which enabled to use, instead of organometallic compounds, carboxylic acid. Carboxylic acids can be used instead of organometallic compounds in cross-coupling. And this is a photoredox catalysis, how it works. It starts with photoexcitation of the iridium photocatalysts, and then photoexcited iridium catalyst is an oxidant. It can oxidize the carboxylic acid. Carboxylic acid, it oxidizes to the radical, and it goes decarboxylation to provide carbon dioxide and this alkyl radical. What happened next? Nickel 0 reacts with aryl halides, oxidative addition take place, and this nickel aryl nickel iodide complex can react with radical species to afford the nickel-free complexes, which further undergo reductive elimination to provide the cross-coupling product and nickel-1 species. And this two catalytic cycle closes by changing the electrons. Iridium gives electron to nickel-1, and in this way, these two catalytic cycles close. Now we asked the question if we can use cyclopropanols instead of carboxylic acids. It would be very interesting to couple them with aryl halides or vinyl halides under similar conditions. But there were one problem, that the oxidation potential of the cyclopropanol is 1.7 volts. And for the iridium catalyst, it's 121. So iridium cannot oxidize cyclopropanol to this radical, cation radical, which can further lose the proton, and this cyclopropyloxy radical can go the ring opening to beta-keta radical. But okay, iridium cannot. But we started to wonder what another catalyst can be used to oxidize this cyclopropanol, and we found that acridinium catalysts very powerful oxidant in the photoexcitate when it is excitated. It is a powerful oxidant. It can oxidize cyclopropanol to cation, radical cation, which can be further undergo isomerization to beta-ket radical. It was great, but it couldn't catalyze the reaction like this, the cross-coupling between cyclopropanol and aryl halide. Acridinium catalyst couldn't do this, but we bear in mind that we need that reaction. And while we were thinking about how to solve the problem, we tried to apply this chemistry, try to apply this reaction, the reaction between photoexcited acridinium catalyst and cyclopropanols. And what we found that the catalytic system consisting of the acridinium catalyst and the diphenyl disulfide can catalyze the reopening isomerization of cyclopropanols to linear ketones. Linear ketones is demanded products because keto group can be found in diverse bioactive compounds, and moreover, keto group is an intermediate in diverse synthesis. This reaction was kind of known, the reaction not under this condition, but in transformation of cyclopropanol to linear ketone, it was known. And the condition reported previously were the use of one equivalent of iron nitrate, iron-free nitrate, and one equivalent of tributylstenan. And the problem was that this non-condition, not only are they not sustainable because they use equivalent amounts of stoichiometric amounts of reagents required, but also this reagent stenan is toxic. Our conditions, they are quite green. They can be considered as green chemistry because there's only catalysts and no toxic reagents. How it works. The question is how it works. Okay, it works this way. The photoexcited catalyst react with cyclopropanol, oxidize it to, it oxidizes it to radical cation, then this radical cation lose proton, and the resulting cyclopropyl radical undergoes reopening, isomerization. At the same time, diphenyl disulfide reacts with visible light. It causes sulfur-sulfur bond cleavage, homolytic bond cleavage, and the phenyl TO radical then reacts with the reduced form of the photocatalysts to obtain thiosulfide anion, which capture proton from the cyclopropanol, and the resulting thiophenol can give this proton to the radical, and this in this way the product forms. This reaction, the scope of this reaction was quite broad. Sensitive groups were tolerated in neutral conditions. That's why the acetal group, for example, was tolerated, and row stereocentrum next to the carbonyl group was tolerated too. Okay, we developed a new method, and then we said, okay, we have an official tool for the this photoexcited acridinium catalyst for the oxidation, so one electron oxidation of cyclopropanol. What else can be used instead of this catalytic cycle, this thiophenol catalytic cycle? And we found out that cobalt catalysis can be used in combination with acridinium as well, and this reaction provided alpha beta unsaturated carbonyl compounds. How it works, the photoexcited, the reduced form of the photocatalyst can reduce the cobalt 2 to cobalt 1. It can capture proton, and this complex can catalyze the H atom abstraction from beta-ket radical to obtain unsaturated products. This reaction, this is the cobalt catalyst. It looks pretty much scary, but it's not. But actually, it's not. It can be synthesized much more easier than the photocatalyst. We used again, the reaction was totally catalytic. And we investigated. We found that I have time. Still have time. We synthesized, according to this method, lots of various enons. They are shown on this slide. This reaction also tolerates sensitive protected hydroxyl groups and other groups. And what else should be said about this reaction? As that we can speak a little bit more about this transformation, about reaction of cobalt H with beta cat radical. The problem is that this is the simplified way of showing this reaction. It's better, more full description of this process is here, because it's more likely that cobalt-2 complex abstract this H atom, and after it's abstract, the alkene forms, and two cobalt 3H complexes, they react with each other to fourth cobalt-2 complexes and hydrogen. And what all else should be said when there are two options which are possible, which protons can be taken away from the molecule by cobalt catalysts. This reaction proceeds under kinetic control. It means that the more sterically available H atom is basically eliminates that from the molecule by this cobalt catalysis. When we used cyclopropanols that contain alkyl chain here, we obtain generally mixtures of enons, alpha beta enons and beta gamma enons. And what should be said here, that there is a room for further investigation, that we require another. We can, in theory, we can control this process by changing the cobalt catalyst. This is something we should work on in the future. Okay, this is how we developed two methods for the redox methods for cyclopropanol transformations. We developed an approach for the isomerization of cyclopropanols to linear ketones and oxidative ring opening of cyclopropanols to enons, oxidative ring opening without an oxidant. There is no oxidant, hydrogen forms in this reaction. Okay, and finally, this is the final project I want to talk about. It was our aim. Our aim was to use cyclopropanol in the similar reaction as Professor Macmillan used, but we couldn't do this. But it was very attractive for us, and it was necessary in synthesis of synchroestrol as well. Finally, why it didn't work? The acridinium catalyst, it oxidizes perfectly cyclopropanol to radical cation, but its reduced form is not as great reductant as iridium-2 species. Okay, this redox potential for the iridium is -1.37, and for this catalyst it is not as strong reducing agent. And we couldn't find the photocatalyst that could be similar in these terms with iridium. So we decided to focus our attention on another. We decided to modify cyclopropanol in order to reduce its oxidation potential and use usual catalytic system for this metal photoredox cross-coupling. We used 4CZ-IPN catalyst. Its properties are pretty much the same as those of iridium catalyst, but it is cheaper. It is an organic photoredox catalyst you can use instead of iridium. And what we required to do, we required to modify cyclopropanol in order to reduce its oxidation potential. For cyclopropanol, it's 1.7. We required something less than 1.35 because its redox potential of the excited forced IPN. And bearing this in mind, we find out an additive. It was titanium isopropoxide that formed such species, and these species were formed, and in the presence of titanium isopropoxide, this reaction proceeded smoothly. The reaction between cyclopropanons and aryl halides, it proceeds smoothly, affording the desired products. Finally, I should mention that this our original idea that this species would be it would be easier to oxidize, then it was 100% wrong, because we measured redox potential for the cyclopropanol and for this complex, and they were the same. So another explanation why titanium isopropoxide works was required, and we explained it this way. We explained it that okay, nickel 0 undergoes oxidative condition with aryl halides, this species forms, and then this nickel 2 reacts with titanium isopropoxide of cyclopropanol titanium complex, and at the same time, for the excited forced IPN reacts with these two molecules, so three molecules kind of somehow reacts to afford the product in which nickel 3, we obtain nickel 3 complex, in which nickel is bound with aryl and with cyclopropanol. This nickel 3 complex, it is typical for nickel 3 alkoxide to undergo homolytic cleavage. And it can give us nickel 2 complex and cyclopropanol radical, which undergo further isomerization to beta kit radicals, and it reacts with aryl nickel complex to afford aryl nickel alkyl nickel 3 complexes. For this complex, it is typical to undergo reductive elimination to afford the products of cross-coupling. Now, this is how we think it works, and Nastasia Vorobyova, the author of this work, is going to give you more details on this research, I think on Thursday, as far as I know. And now I would like to say that we investigated the scope. I will not discuss it. Nastasia will tell you more about this reaction. And what I want to say is that we finally managed to carry out, I told at the beginning of my talk that we required the reaction between the cyclopropanol and vinyl halides. This transformation, alkylation of cyclopropanols was elusive, but we did it. Now it is possible to react cyclopropanol with vinyl halides to obtain gamma delta unsaturated ketones. And at the end of my talk, I would like to say a few words about applications. We've just developed these new tools, and we started to employ them. And the first place where we employed it, it was the ring opening, the synthesis of this ketone, the ketone required for the preparation of sphingnoacetal. This reaction under known condition, it led to mixtures. And moreover, toxic reagents were necessary. When we used our conditions, 85% yield was achieved. It proceeded really smoothly. Another task was the synthesis of steroids with diverse side chains, and using our developed by our research group methods, we managed to obtain new steroidal compounds which were toxic toward cancer cells and CR7. And this is it. I would like to thank my students who did this amazing work, thank my amazing students, and I would like to thank you for your kind attention. I'd like also thank everybody who supported me and us in this project. Thank you very much.
Okay, thank you, Alexey, for nice presentation showing how you can activate cyclopropanols. Let's thank our speaker. And we have a chance to ask questions to speaker. No question. Can I ask you?
Oh, yes, of course you can.
In the title of your presentation, it is shown that you are synthesizing bioactive compounds. What most bioactive compounds you synthesize, and what is the target for these compounds?
I would like to say that now we just began, we just started to apply these methods in synthesis. And the most active, you're talking about most active and most interesting compound is the compound. This work is still ongoing, is the synthesis of this molecule, this phencoesterol. Can you see my screen? Oh.
Yes, we see.
Yes, you see. So this molecule is phencoesterol. This is a steroid isolated in 2014, and it is it possesses anti-cancer activity, and moreover, it's an histone.
What is the receptor?
Histone acetyltransferase inhibitor.
Okay.
Yeah.
Okay. Thank you very much again for a nice presentation.